Hi, this is exercise 6C on hyperbolics. Now, it's actually from the Year 13 textbook, so I'm very conscious when going through this that there's going to be a few bits and bobs that you haven't necessarily had explained before, because we're doing this in a funny order. So I might spend longer on this than I would otherwise have done. That's not a problem. But just bear that in mind as we're going through it. It might end up taking 2 PowerPoints instead. So on this one, it's a bit cheekily, it says reminder. I think for you, this isn't really so much a reminder. It's the first time you're going to see it. Let's first of all define what are called the inverse or the reciprocal trigonometric functions, rather. So the reciprocal trigonometric functions are what you get if you do 1 divided, say, by sine x. And 1 divided by sine x is called cosec x. It's got its own name. Now, interestingly, you don't get this on your calculator. If you ever want to do cosec x, you've got to do 1 divided by sine. But it's got its own name, and you'll see it loads. It's not just sine that has its reciprocal function. So 1 divided by cos x, or often called sec x. And I always think these are kind of the wrong way around. This is the S, the star, and this is the C, and this is the C, and this is the S. So I always think they're the wrong way around. The good news is that 1 divided by tan x has got its own name, and at least there's a bit of logic here, in as much that this is called cot x. It actually stands for cotangent, but the cot, then you can see, has got a T in it, and that's our key to remembering. The third letter here is a T, and it was 1 divided by tan. The third letter here is the C, and it was 1 divided by cos. Third letter here is the S, and it's 1 divided by sine. So these 3 functions are very useful. We will at some point have to try to differentiate and integrate functions. Probably not today, but we'll look at that in due course. Now, first of all, I've written down here cos squared plus sine squared. This is an identity we've seen in normal maths. We should know that's 1. Oh, there was another one, wasn't there? You saw that tan x can be written as sine x divided by cos x. So these are quite useful, these identities, in normal maths and in this maths. Now, if I would choose to divide all of these things, if I divide all of these by cos squared, so if I divide cos squared by cos squared, you won't be surprised that I get 1. And notice I'm then going to go through the entire identity and go sine squared divided by cos squared. Well, I've written that over here. Look, sine over cos is tan. So sine squared over cos squared is tan squared. That's all that says. So I'm dividing that by cos squared, divide that by cos squared, and I get this tan squared because of this rule down here. And the last one, which I haven't written down, is 1 divided by cos squared. And that's why I've done all this stuff up here. Look, 1 divided by cos is sec. It's this new function. So therefore, when I divide by cos squared, I get sec squared. So this is a new function and a new identity. But this is very useful identity. You'll be amazed how often you end up using that. So that is one to learn. Now, I got that equation, or identity rather, by starting off with the really important one. This is the one that comes up so often. And I chose to divide everything by cos squared, the first thing. If instead I divide by sine squared, well, let's see what happens. I get cos squared divided by sine squared. Now that's actually different from what I've got here. I've got sine over cos. So what would I get if I get cos over sine? And you can see it's the upside down version of this. So really, I suppose it's got to be the upside down version of the tan. And the upside down version of the tan is called cot. So again, that's where that comes from. Cos squared divided by sine squared is cot squared. Sine squared divided by sine squared, oh, that's 1. That's fair enough. And 1 divided by sine squared, that should be up here again. If we look up here, 1 divided by sine is cosec. So 1 divided by sine squared is cosec squared. Are they vital for us in a bit? Well, possibly. We might need to see some of these in a bit. So we'll come on to those in a bit. And there's 3 others I'm going to just really, well, this one's easy. this one just comes from a rearrangement of this. There are times you see that when we differentiate or integrate these weird functions, and at the moment you're thinking, why would I want to do that? But in due course we'll need to, particularly in normal maths, but also in further maths. When we do this, cos squared, you can't integrate cos squared in its present form. There's, we don't like that. So what we do is we rewrite it in this new form. Now, by the way, there's the answers for that. So we rewrite it in this new form over here. So cos squared equals this. Now, you can obviously multiply that out. The bracket, sometimes it helps, sometimes it's better left like this. But it's worth you just writing down that cos squared x is a half of 1 plus cos 2x. Later on we prove this. It's actually not too hard to prove at all, and kind of involves this big identity over here, which I've written down. Cos squared plus sine squared is 1. The second one is actually very similar. What do I need to change sine squared into if I want to differentiate or integrate? Well, I actually want to do this. It's a half of 1 minus cos 2x. So just write it down, learn it for now, we'll prove it later. And as I say, we do prove it later because it's quite a nice proof. And then tan squared x, well, I just think it's fairly obvious. You move the 1 over and then you get a tidier version of what I've written there. Sec squared minus 1. So I've got one identity here that we definitely need to know. One that I've told you in normal maths. I've introduced 3 reciprocal functions, 1, 2, 3. We need to know all those. These rearrangements are very important, particularly in the middle one. Right, that's more important than the bottom one, but occasionally we do see the bottom one. And these 3 things, we want these for when we are differentiating and integrating these weird functions. Not yet. And the reason why it's not yet, because we are predominantly now going to look at some proofs of hyperbolics. And what I want then is, first of all, cosh, you should remember that cosh is a half of e to the x plus e to the minus x. And I'm going to add to it plus half of the shine, which is e to the x minus e to the minus x. So this is what we're after. So shine, you need to know, is this. Cosh, you need to know, is this. We saw this last time. And if I multiply out the brackets, I get a half e to the x plus a half e to the minus x plus a half e to the x minus a half e to the minus x. And just looking at that, that's a minus, that's a plus, and they're exactly the same, but they therefore cancel each other out. And what's left is you've got a half e to the x plus another half e to the x, and that is e to the x, which of course is what I wanted. So that's the first one done. The second one, well, it's exactly the same on the left hand side, apart from it's got a minus, and it's got a slightly different answer on the right. So what do I want to do? Well, let's write it out in the brackety form again. Half e to the x plus e to the minus x minus a half bracket e to the x minus e to the minus x. So presumably I'll go through exactly the same thing. Alright, half e to the x plus a half e to the minus x minus a half e to the x, and minus becomes a plus. So that's a plus when I do that multiplication, e to the minus x. And this time this one cancels with this one. I've got a half of that and half of that, so I've got a whole one, e to the minus x. So again, that one I think was quite straightforward. Now, alright, so he wants me to prove cosh squared minus shine squared. I suppose what I'm going to have to do is to look at what cosh is. And cosh is a half e to the x plus e to the minus x. And I'm going to have to square that. And then I'm going to take away a half e to the x minus e to the minus x squared again. And the question is, what does that give me? And eventually, of course, I want to give it equal 1, but it's certainly not there yet. Well, a half squared is easy. I can do that. It's a quarter of something. And then if I multiply out this bracket, I get e to the x plus e to the minus x times by e to the x plus e to the minus x. And presumably I get exactly the same thing over here. put that in a square bracket so I don't get confused. Minus square bracket, half squared is a quarter again, and it's e to the x minus e to the minus x times by e to the x minus e to the minus x. So what's this give me? It gives me a quarter. Now, basic powers, that gives me e to the 2x. E to the x times e to the minus x. We add the powers, so that gives me nothing when I add it. So that's e to the 0. Now e to the 0, you should remember, is 1. So that's plus 1. But I get another one like that here, so that's plus 2. And I should put this in the bracket as well. And what's the last one? Gives me e to the minus x times by e to the minus x is e to the minus 2x. Minus a quarter of, and again I get the same thing, e to the 2x. Now I get minus e to the 0, so that's minus 1 minus another 1, that's minus 2, and that times by that is minus 1 minus is plus, e to the minus 2x. I think that's right. So let's tidy up, get rid of some brackets. I get a quarter e to the 2x. Oh, I'll get another quarter. Oh, no, I don't. I'll take my time on that because I was just about adding together, but I don't. 2 lots of a quarter is a half plus a quarter e to the minus 2x. Okay, that's done. And I'm going to subtract a quarter e to the 2x. In fact, I'll get rid of the bracket and I'll just say that's minus, but this in minus times a minus is going to be a plus 2 quarters, or a half again. And the last one, it's a minus here, times a quarter times that is minus a quarter e to the minus 2x. And importantly, that cancels with that. That cancels with that. I'm left with a half plus a half, which equals 1. God, I got there in the end. Got another one here, cos 2x. Now, I suppose I could do this by saying, well, I know what cos is. It's a half of e to the x, and I'm just going to write e to the 2x plus e to the minus 2x. And what I want to do there is perhaps say, well, I'm almost tempted to have a look at the right-hand side on this, otherwise I think I might struggle. So I'm just going to put this to one side for a bit and say, okay, I know what the left-hand side equals. But let's go over here, cos squared. Well, that's a half of, did we just do cos squared just now? Yeah, we did, didn't we? We squared the cos, and we got this. So let's write that down. E equals, when I squared it, it was a quarter e to the 2x. So I don't really want to do all that again. And it was then plus a half plus a quarter of e to the minus 2x. And did I do sine squared as well? I did, didn't I? Yeah, so ignore this minus, it's a quarter e to the 2x. Everything I think was the same, but apart from it said minus a half in the middle, plus e to the, a quarter e to the minus 2x. So what does that give me? A quarter plus a quarter is a half e to the 2x. And the halves cancel, and it's a quarter plus a quarter again, which is a half. So you can clearly see that this is working. Because that is equal to that. So you could then say equals cos 2x. Done. The last one I think is going to be a very similar one. Sine 2x. I'm going to start on the right hand side. We had much more joy over this last time. So I'm going to write 2 times a half of e to the x minus e to the minus x times by a half of e to the x plus e to the minus x. Well, the first thing I notice is 2 times a half disappears, but I've still got a half left here. And I'm going to run out of time here, just realise. So I'm going to leave you to do it. What you're asked to eventually is to get to a solution where you go, the same as sine 2x. So it will look like this, like this expression with 2x in. Have a go for me, There's a summary of all the identities, and there's the exercise. Okay, thank you and good luck.